Hello, in this lecture we'll find out the area of the green shape. In the drawing we have a circle inside a quarter circle. In addition, we know that the radius of this small circle is equal to the square root of 2 units, and our mission is to find out the area of this green shape. So first of all, we will define the relevant points to this question with letters. So we define this point as A, we define this point as B. This point is the center of the quarter circle. We define the center of the quarter circle as point O. We define this point as C. We define this point as D. This point is the touching point between the circle and the quarter circle. We define the touching point as E. And finally, we define the center of this small circle as F. In the next step, we will join points F and C together by a straight line. What is the definition of line segment FC? Line segment FC starts from point F, that is the center of the small circle, and ends at point C, that is the point on the small circle itself. Therefore, FC is the radius of this small circle, that equals to the square root of 2 units, according to what is given as the question. Can implement here rule 1. Repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So, in the drawing we have a circle, and we have, this is tangent AB, that is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM is equal to R, that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule, rule 1. We can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius FC that is drawn to point C, that is the point of tendency of tangent OD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius FB of the small circle that is drawn to point B, that is the point of tendency of tangent AD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AD, tangent AO, this is tangent AO, will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So inside the small quadrilateral BFOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, the sum of those 4 angles they must be equal to 360 degrees. According to the rule, the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing fourth angle here must be equal to 90 degrees in its side. Again, in order to complete the sum of the angles inside the small quadrilateral PFOC to 360 degrees, the missing angle here must be equal to 90 degrees. So inside the small quadrilateral BFOC, we have 4 right angles. Any quadrilateral that has 4 right angles must be this rectangle if not a square. So we will relate to this small quadrilateral BFOC with 4 right angles as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side BF must be equal to the opposite side OC in rectangle BFOC. But BF equals to the square root of 2, therefore OC must be also equal to the square root of 2 units in its length. Likewise, according to the sum rule in rectangle BFOC, side FC must be equal to the opposite side BO. But FC is square root of 2, therefore the opposite side BO must be also equal to the square root of 2 units in its length. In the next step, we join points F and O together by a straight line. By joining points F and O, we created the right triangle FBO. In the right triangle FBO, those two sides are both equal to the square root of 2 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other. So if we define the size of this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. And especially it is true in the right triangle FBO. So which angles we have inside the right triangle FBO? We have here this angle equals to 90 degrees. This angle equals to alpha, and the other angle also equal to alpha, so 90 degrees plus 2 alpha. In total, they must be equal to 180 degrees according to the rule that I mentioned. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. Here we divide this equation by 2, and finally we get that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. So actually, this angle alpha is equals to 45 degrees in its size. And this angle is also angle alpha, is equal to 45 degrees. In the next step, we will implement the Pythagoras theorem in the same right triangle, this right triangle FBO. So, in the right triangle FBO, by PT is an abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in the right triangle FBO, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, the hypotenuse is OF, therefore the square of the hypotenuse is OF square, and it must be equal to OB square plus BF square. repeat again. Moving to the Pythagoras theorem. In the right triangle FBO, OF squared equals to OB squared plus BF squared. So OF squared, which is the square of the hypotenuse, equals to OB squared. OB is square root of 2, therefore OB squared is square root of 2 squared, that is 2, plus BF squared. BF is also equals to the square root of 2, therefore BF squared is square root of 2 squared, that is 2. So we conclude further that OF squared, the square of the hypotenuse, equals to 2 plus 2, that is 4. OF squared equals to 4. Here we take a root out of this equation and finally we get that OF equals to the square root of 4, that is 2. So we found out that the length of the hypotenuse OF in the right triangle BOF is equals to 2 units. In the next step, I will present to you a new rule and we'll implement the new rule in our drawing. The new rule is rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass through their touching point. In the drawing, we have two circles. The small circle is located inside the big circle, and therefore we have here an internal notch between those two circles at point P. That is to say, the two circles touching each other internally at point P. So whenever you have an internal notch between two circles, you can implement this rule, rule 9. So according to rule 9, this rule 9, the straight line that connects their centers together. So here, the center of the big circle is here at point E. The center of this small circle is here at point M. And the straight line that connects their centers together is the straight line OM. According to this rule, rule 9, the straight line OM must pass through point P. Okay, the straight line OM must pass through point P, or OMP is one straight line. Again, OMP is one straight line. So we can actually implement this rule 9 in our drawing. Why? Because in our drawing, the small circle is located inside the big quarter circle, and they touch each other internally at point A. Therefore, we can implement here rule 9. The center of the big quarter circle, or the center of the big circle, here is point here. It is here at point O. The center of this small circle is here at point F, and the straight line that connects their centers together is the straight line OF. According to rule 9, the straight line OF must pass for point E. Or OFE is one straight line. Again, OFE is one straight line. So we'll extend the straight line OF until it touches point E. So I write it here that OFE is one straight line. Line segment OFE is one straight line. But what is the other definition of line segment OFE? Okay, what is the other definition of this line segment OFE? Point O is the center of the big circle, point E is a point on the big circle itself. This is exactly the definition of a radius. Therefore, line segment OFE is also the radius of the big circle. We define the radius of the big circle as capital R. Capital R is the radius of the big circle. So capital R equals to OFE. And what is the length of the radius of the big circle, capital R? Because of the fact that we know that OFE is one straight line, it means that the length of this line segment OFE, that is the radius of the big circle, will be equal to OF plus FE. Will be equal to OF plus FE. Repeating it, the length of this line segment OFE equals to OF plus FE, because OFE is one straight line. So what is the length of line segment FE? We know that point F is the center of the small circle, point E is the point on the circle, on the small circle itself. Therefore, FE is the radius of the small circle that is equal to the square root of 2 units. So FE equals to the square root of 2 units in its length. Therefore, the radius of the big circle, capital R, equals to OF, that is 2, plus FE, that is square root of 2. In conclusion, we found out that capital R, that is the radius of the big circle, equals to 2 plus square root of 2 units in its length. We will define the intersection point between line segment OFE and this small circle. We define this point as H. So we know that OFE is one straight line. If OFE is one straight line, it means that HFE is also one straight line, because HFE is part of OFE. Okay, so HFE is a straight line that touches the small circle at 2 points. Touches the small circle here at point H, and another point is here at point E. Any straight line that touches the circle at 2 points is defined as a chord. So we know that HE is a chord, or HFE is a chord, but HFE is a chord that passes from point F, that is the center of the small circle, and we know that any chord that passes for the center of the circle must be the diameter of the circle. Okay, therefore HFE is the diameter of the small circle, and FE is the diameter of the small circle, and we know that the diameter of any circle bisects the circle into 2 halves. Each half is half of the area of the circle. So this part is half of the area of this small circle, and the other part is the second half of the area of this small circle. So this shape is a semicircle. because it is half of the area of this small circle. So this shape is a semicircle because edge F3 bisects the small circle into two halves. This is the first half that is defined as a semicircle. So if we're going to find out that this shape edge BE is a semicircle, that's one half of the small circle. So it is a semicircle. In the next step, I will present to you a new notion and we'll implement it in our drawing. What is a sector? Here we have a circle and this green shape AOB is a sector. So a sector is defined as a part of a circle. If we look at this circle as a cake, then a sector is one slice of this cake. Okay? This green sector AOB consists of two legs. The first leg is AO and the second leg is BO. Both those two legs are the radii of this circle that is equal to R. And the angle between those two legs AO and BO of the green sector AOB is angle theta. Okay, and the area of this green sector AOB equals to pi r squared, that is the area of the circle, times theta over 360 degrees. And theta is the angle between the two legs AO and BO of this green sector AOB. In conclusion, found out that the area of a sector equals to the area of the circle that contains the sector times theta over 360 degrees. Theta is the angle between the legs of the sector. Okay. So our mission is to find out the value of this green shape, or the value of this green, the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape equals to the area of the big sector AOE. The big sector AOE is part of the big circle. This rounded line above AOE is the sign for a sector. It means sector AOE. And the two brackets is the sign for the area. So this expression in total equals, it is actually means the area of sector AOE. Okay. So the area of the green shape in total will be equal to the area of the big sector AOE minus the area of this small semicircle minus the area of shape B edge O. So that minus the area of the orange shape B edge O. Repeat again. The area of the green shape equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this orange shape BHO. The area of the green shape equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape BHO. So first of all, we find out the area of the big sector AOE. Repeat again that the area that the big sector AOE is part of the big circle, and we know that the area of any sector equals to the area of the circle that contains the sector. So the area of the big circle equals to pi times capital R square. Again, the area of the big circle equals to pi R square because capital R is the radius of the big circle times theta, that is the angle between the legs of this sector AOE. This is the angle between the legs of the big sector AOE. We already found out that this angle equals to 45 degrees in its size, so it is 45 degrees over 360 degrees. So the area of the big sector AOE is equals to pi times capital R square. So it is pi, and we already found out that capital R equals to 2 plus square root of 2. Therefore capital R square will be equal to 2 plus square root of 2 square. And we have here 45 degrees over 360 degrees, it is 1 over 8. So we divide the area of the big circle by 8. So it is pi times 2 plus square root of 2 square. What is the value of 2 plus square root of 2 square? According to the algebraic identity that a plus b square equals to a square plus b square plus 2 times a and b, we get that 2 plus square root of 2 square equals to 2 square, that is 4, plus square root of 2 square, that is 2, plus 2 times 2 times square root of 2 divided by 8. So the area of the big sector AOE will be equal to pi. Inside the brackets we have 4 plus 2, that is 6, plus 2 times 2 is 4, so this expression in total will be equal to 4 plus square root of 2 divided by 8. Here we divide both the numerator and the denominator of this expression by 2, and we get that this expression will be equal to, we divide it by 2, it will be equal to pi. Inside the brackets we have 6, 6 over 2 is 3, plus 4 times square root of 2 over 2 is 2 times square root of 2. And we have to divide also the denominator 8 by 2. 8 over 2 is 4. So, in conclusion, we found out that the area of the big sector AOE is equals to pi times 3 plus 2 times square root of 2 over 4 square units. In the next step, we find out the area of the small semicircle. The small semicircle is half of the small circle, and the area of the small circle is pi r squared. If we divide the area of the small circle by 2, we get the area of the small semicircle. So the area of the small semicircle equals to pi r squared over 2. So it is pi r equals to the square root of 2 units according to what is given as the equation. Therefore r squared is square root of 2 squared, that is 2, divided by 2. 2 over 2 is 1, so we left only with pi. In conclusion, we found out that the area of the small semicircle is equal to pi square units. And finally, we find out the area of the green shape, the area of this orange shape, BHO. What is the area of the orange shape, BHO? From the drawing, it is very easy to see that the area of the orange shape BHO equals to the area of the right triangle FBO minus the area of the small sector FBH, this small sector FBH. Repeat again. The area of the orange shape BHO equals to the area of the right triangle FBO minus the area of the small sector FBH. The small sector FBH is part of the small circle. This small sector FBH is part of this small circle. So we have to find out the area of triangle FBO, the right triangle FBO. What is the area of the right triangle FBO? We know that the area of any triangle equals to the base of the triangle times the height to the base over 2. So here in this right triangle FBO, the two perpendiculars, each of them is equal to the square root of 2. So the height equals to the base, they are both equal to the square root of 2. Okay? So the base is equal to the square root of 2 times the height, that is also square root of 2, divided by 2. So the square root of 2 times square root of 2 is 2, and 2 over 2 is 1. In conclusion, we found out that the area of the right triangle FBO is equal to 1 square unit. In the next step, we find out the area of the small sector FBH. repeat again that this small sector FBH is part of the small circle, and we know that the area of any sector equals to the area of the circle that contains the sector. The small circle contains the small sector FBH, therefore the area of the small circle is pi r square times the angle between the legs of this sector FBH. The angle between the legs is 45 degrees. So it is 45 degrees over 360 degrees. So if we found out that the area of the small sector FBH equals to pi r squared times 45 degrees over 360 degrees. So it is pi and r is square root of 2, therefore r squared is square root of 2 squared, that is 2. And we have to multiply it by 45 degrees and divide it by 360 degrees. 45 degrees over 360 degrees, it is 1 over 8. So we have to divide the area of the small circle 2 pi by 8. So here we divide both the numerator and the denominator of this expression by 2. 2 pi over 2 is pi, and 8 over 2 is 4. So in conclusion, we found out that the area of the small sector FBH is equals to pi over 4 square units. So in total, the area of the orange shape BHO is equal to the area of the right triangle FBO, that is equal to 1 square unit, minus the area of the small sector FBH, that is equal to pi over 4 square units. So in total, the area of the orange shape BHO equals to 1 minus pi over 4 square units. Okay. So I repeat again that our mission is to find out the area of this strange shape. The area of the green shape is equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this orange shape BHO. We have already found out the area of each shape. Repeat again, the area of the green shape equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape BHO. So the area of the green shape will be equal to the area of the big sector AOE. We already found out that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units minus the area of the small semicircle. We have already found out that the area of the small semicircle is equals to pi square units, so that minus pi minus the area of the orange shape BHO, and we already found out that the area of the orange shape BHO equals to 1 minus pi over 4 square units. So actually, this expression, the area of this expression, is actually the area of the green shape. So we simplify this expression in order to get the area of the green shape in terms of numbers. So here we'll open the brackets. We have pi times 3 is 3 pi plus 2 times square root of 2 times pi over 4 minus pi. Here we'll open the brackets. We have minus before the bracket, so it will be here minus 1, and here we have minus times minus is plus, so it is minus 1 plus pi over 4. So the area of the green shape in total will be equal to, we have 3 pi plus 2 times square root of 2 pi over 4. And here we have minus pi plus pi over 4 is minus 3 quarters pi. Minus 1. Here we multiply minus 1 by 4 and then we divide it by 4 in order to overcome factor with the other two expressions. So minus 1 times 4 is minus 4 divided by 4. So we have here 3 pi minus 3 pi is 0. After we cancel 3 pi, we left only with 2 times square root of 2 pi minus 4 over 4. Here we divide both the numerator and the denominator of this expression by 2, and we get that 2 times square root of 2 pi over 2 is square root of 2 pi, minus 4 over 2 is minus 2, and we have to divide also the denominator 4 by 2. 4 over 2 is 2. So in conclusion, we found out that the area of the green shape is equal to square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, the area of the green shape will be equal to 2.114 square units. Repeat again. The area of this green shape is equal to either square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, the area of this green shape equals to 2.114 square units. Okay, so in the next step, I'll summarize the lecture. In this lecture, we found out the area of this green shape. In the drawing, we have a circle, a small circle inside this quarter circle. In addition, we know that the radius of this small circle r equals to the square root of 2 units. Again, our mission is to find out the area of this green shape. So first of all, we defined the relevant points to this question with letters. We define this point as A, this point as B. This point is the center of the quarter circle. We define the center of the quarter circle as O. We define this point as C. We define this point as D. This point is the touching point between this small circle and the big quarter circle. We define the touching point as E. And finally, we define the center of this small circle here, this point as F. Then we join points F and C together by a straight line. What is the definition of line 7 FC? Line 7 FC starts from point F, that is the center of this small circle, and ends at point C, that is the point of this small circle itself. So this is exactly the definition of a radius. FC is the radius of this small circle, that is equal to square root of 2 units according to what is given as the question. The radius FC of this small circle is drawn to point C, that is the point of tendency of tangent OD of this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius FE of this small circle that is drawn to point. We have the radius FB of this small circle that is drawn to point B, that is the point of tendency of tangent AO with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to the same rule, rule 1. So inside the small quadrilateral BFOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing fourth angle here must be equal to 90 degrees in its side. Again, in order to complete the sum of the angles inside this small quadrilateral BFOC to 360 degrees, the missing angle here must be equal to 90 degrees in its side. So we found out that inside this small quadrilateral BFOC we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this small quadrilateral BFOC is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, in a rectangle BFOC, side BF must be equal to the opposite side OC. But BF equals to the square root of 2, therefore OC must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, in rectangle BFOC, side FC must be equal to the opposite side BO. But FC equals to the square root of 2, therefore BO must be also equal to the square root of 2 units in its length. So actually found out that quadrilateral BFOC is not a rectangle, but a square, because all of its sides are equal to each other. Its side of this square is equal to the square root of 2 units in its length. In the next step, we join points O and F together by a straight line. By joining points O and F, we get the right triangle OBF. Inside this right triangle OBF, we have those 2 sides that are both equal to the square root of 2 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those 2 angles that are located in front of those 2 equal sides must be also equal to each other. So if we define this angle as alpha, then the other angle must be also equal to alpha, because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have inside this small right triangle OBF? We have, this is angle alpha, this is also angle alpha, and this is angle 90, this is equal to 90 degrees. So 2 alpha plus 90 degrees, in total it must be equal to 180 degrees according to the rule that I mentioned. We subtract 90 degrees from this equation, and found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. We divided this equation by 2 and finally found out that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha, that is equal to 45 degrees, and this is also angle alpha, that is also equals to 45 degrees in its size. In the next step, I presented to you a new rule, and we implemented the new rule in our drawing. According to the new rule, if two circles touch each other internally, then the straight line that connects their centers together must pass through their touching point. In this drawing, we have an internal notch between those two circles, that is to say they are touching each other internally at point P. Point P is their touching point. So whenever you have an internal notch between two circles, you can implement rule 9. And according to this rule 9, the straight line that connects their centers together must pass through their touching point. The center of this big circle is here at point O. The center of this small circle is here at point M. And the straight line that connects their centers together is the straight line OM. And according to this rule 9, the straight line OM must pass through point P. That is their touching point. Or OMP is one straight line. Again, OMP is one straight line. We can implement rule 9 in our drawing. Why? Because in our drawing, we have an internal notch between the small circle and the big quarter circle. That is to say, the small circle touches the big quarter circle internally. First of all, the small circle is located inside the big semicircle and the big quarter circle, and they touch each other internally at point E. Therefore, so there is an internal notch between the small circle and the big quarter circle, therefore we can implement the rule 9. According to rule 9, the straight line that connects their centers together must pass through their touching point. The center of the big quarter circle is here at point O. The center of this small circle is here at point F, and the straight line that connects their centers together is the straight line OF. And according to rule 9, the straight line OF must pass through point E. Again, the straight line OF must pass through point E. Or OFE is one straight line. OFE is one straight line according to rule 9. Here OFE is one straight line. But what is the definition of the straight line OFE or line segment, the straight line OFE? What is the other definition of the straight line OFE? The straight line OFE starts from point O, that is the center of the big quarter circle, and ends at point E, that is the point of the quarter circle itself. This is exactly the definition of a radius. Therefore, OFE is the radius of the quarter circle. We define the radius of the quarter circle, that is also the radius of the big circle, as capital R. And capital R is the radius of the big circle. So, capital R equals to OFE. Capital R equals to OFE, and we know that OFE is one straight line, therefore the length of line segment OFE, that is also the radius of the big quarter circle, it is equals to OF plus FE. Again, OF equals to OF plus FE. What is the definition of line segment FE? Line segment FE starts from point F, that is the center of the small circle, and ends at point E, that is the point of the small circle itself. This is exactly the definition of a radius. Therefore, line segment FE is the radius of this small circle, that is equals to the square root of 2 units, according to what is given us the question. So FE equals to the square root of 2 units. So OFE in total equals to OF plus FE. OF equals to OF plus FE. OF is 2 and FE is square root of 2. So OF is 2 plus square root of 2. That is to say, capital R equals to 2 plus square root of 2 units in itself. So the radius of the big circle and also the radius of the big quarter circle, capital R equals to 2 plus quarter of 2 units in its length. So we know that OFE is one straight line. We defined the intersection point between the straight line OFE with this small circle as edge. So if OFE is one straight line, it means that edge FE is also one straight line because edge FE is part of OFE. So we know that edge FE is one straight line, line segment edge FE is one straight line, but line segment edge FE touches this small circle at point E, here and here at point H. Any straight line that touches the circle at 2 points must be a chord. So edge FE is a chord inside this small circle, but it is a special chord that passes from point F, that is the center of this small circle. And we know that any chord that passes through the center of a circle must be the diameter of the circle. Therefore, edge FE is the diameter of this small circle. Here, edge FE is the diameter of the small circle. And we know that any diameter of any circle bisects the circle into two halves. This is the first half, and this is the second half. And we know that half of a circle is defined as a semicircle. So concluding further that this shape is a semicircle. Then I presented to you the notion of a sector. What is a sector? A sector is part of a circle. This is the circle, and the green shape A or B is a sector. So if we look in this circle as a cake, then the sector A or B is one slice of this cake. Okay, so here the green sector A or B consists of two legs. The first leg is AO and the second leg is BO. Okay, both legs AO and BO, they are the radii of this circle that is equal to R. And the angle between the legs of this green sector AOB is theta. And what is the area of this sector AOB, the green sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is actually pi r squared, times theta, that is the angle between the legs of the green sector AOB, over 360 degrees. I repeat again, the area of a sector equals to the area of the circle that contains the sector times the angle between the legs of the sector over 360 degrees. You can implement actually the new rule here of the area for a sector in our drawing. Actually, our mission is to find out the area of this green shape. From the drawing, it is very easy to see that the area of this green shape in total equals to the area of the big sector AOE. The big sector AOE is part of the big circle, so it is the area of the big sector AOE minus the area of the small semicircle minus the area of this orange shape. Again, the area of the green shape in total is equal to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape BHO. Okay, so first of all, we find out the area of the big sector AOE. Again, the area of any sector equals to the area of the circle that contains the sector. This sector is contained by the big circle, so the area of the big circle is pi times capital R squared, pi times capital R squared, times the angle between the legs of this big sector. This is the angle between the legs of this sector AOE, that is actually equals to 45 degrees over 360 degrees. So in total, the area of the big sector AOE equals to pi r squared times 45 degrees over 360 degrees. we have already found out that capital R equals to 2 plus square root of 2. Therefore, capital R square equals to 2 plus square root of 2 square. And we have to multiply it also by 45 degrees over 360 degrees. 45 degrees over 360 degrees, it is 1 over 8. So we have to divide the area pi times 2 plus square root of 2 square by 8. So it is pi, and we have 2 plus square root of 2 square equals to 2 square, that is 4, plus square root of 2 square, that is 2, plus 2 times square root of 2 divided by 8. So we have there the big sector A equals to, we have here pi, inside the brackets we have 4 plus 2, that is 6, and here we have 2 times 2, that is 4, so in total this expression equals to 4 times square root of 2, all divided by 8. 4 times square root of 2 divided by 8. Here we divided both the numerator and the denominator of this expression by 2, and found out that after we divide it by 2, we will get the pi, and inside the brackets we have 6 over 2 is 3, and we have also 4 times square root of 2 over 2 is 2 times square root of 2, and we have to divide the denominator 8 also by 2, so 8 over 2 is 4. So in conclusion, we found out that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units. In the next step, actually we found out the area of this small semicircle. The small semicircle is half of the small circle. And you know that the area of the small circle equals to pi r square. And therefore the area of the small semicircle will be equal to pi r square over 2. R is equals to the square root of 2, therefore r square is square root of 2 squared, that is 2. So in total, the area of the small semicircle equals to 2 pi, that is the area of the small circle, over 2. 2 over 2 is 1, so we left only with pi. In conclusion, we found out that the area of this small semicircle, it is equals to pi square units. And finally, we found out the area of this orange shape, the area of this orange shape BHO. What is the area of the orange shape BHO? From the drawing, it is very easy to see that the area of the orange shape BHO equals in total to the area of the right triangle BOF minus the area of this small sector FBH. Click again. In total, the area of the orange shape BHO equals to the area of the right triangle FBO minus the area of the small sector FBH. The small sector FBH is part of the small circle. So the area of the right triangle FBO equals to the area of any triangle equals to the base of the triangle times the height to the base over 2. Here the base equals to the height, they are both equal to the square root of 2 units. So the base is square root of 2 and the height is also square root of 2 divided by 2. Square root of 2 times square root of 2 is 2 and 2 over 2 is 1. So in conclusion we found out that the area of this right triangle FBO equals to 1 square unit. And we have to subtract from the area of the right triangle FBO the area of this small sector FBH. Again, this small sector FBH is part of this small circle. And we know that the area of any sector equals to the area of the circle that contains the sector. The small circle contains the small sector, and we know that the area of the small circle equals to pi r square times the angle between the legs of this small sector FBH. The angle is 45 degrees. So it is 45 degrees over 360 degrees. So what is the value of pi r square? R is square root of 2, therefore r square is square root of 2 squared, that is 2. So in total the area of the small circle equals to 2 pi, and 45 degrees over 360 degrees, it is 1 over 8. So we have to divide the area 2 pi, the area of the small circle 2 pi by 8. Here we divided both the numerator and the denominator of this expression by 2. 2 pi over 2 is pi, and 8 over 2 is 4. In conclusion, we found out that the area of the small sector FBH is equals to pi over 4 square units. Therefore, in total, the area of the orange shape BHO equals to the area of the right triangle FBO, that is 1, minus the area of the small sector FBH, that is pi over 4. So the area of the orange shape in total equals to 1 minus pi over 4 square units. I repeat again that our mission is to find out the area of this green shape. So we already found out that the area of the green shape equals to the area of the big sector AOE minus the area of this semicircle minus the area of this orange shape. Repeat again. The area of the green shape in total equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape BHO. We have already found out that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units minus the area of the small semicircle, that is pi, minus the area of the orange shape BHO, that is 1 minus pi over 4. So in total, this expression is the area of the green shape, that is the area that we are looking for. So we just simplified this expression in order to find out the area of the green shape in terms of numbers. So here we have pi. We open the brackets here. It will be 3 pi plus 2 times square root of 2 pi divided by 4. And we have here minus pi minus, we have here brackets, we open the brackets, we have minus before the brackets, so here we have minus 1, and minus times minus is plus, so it is in total minus 1 plus pi over 4, minus 1 plus pi over 4. So here we have 3 pi plus 2 times square root of 2 pi, and we have here minus pi plus pi over 4 is minus 3/4 pi, minus 3/4 pi, and we have here minus 1, we multiply minus 1 by 4, then we divide it by 4 in order to common factor with the other two expressions. So minus 1 times 4 is minus 4, divided by 4. So here we have 2 pi, 3 pi minus 3 pi is 0. After we cancel 3 pi, we left only with 2 times root of 2 pi minus 4 over 4. Here we divided both the numerator and the denominator of this expression by 2. 2 times root of 2 pi over 2 is square root of 2 times pi, and minus 4 over 2 is minus 2. We have to divide the denominator of 4 also by 2. 4 over 2 is 2. So in conclusion, we found out that the area of this green shape is equal to either square root of 2 pi minus 2 over 2 square units, or in terms of numbers, the area of this green shape is equal to 2.114 square units. Okay, thank you very much.